Hey everyone, welcome to The Explainer. I am absolutely thrilled to be jumping into today's topic with you. We're looking at something that is literally game-changing for how enterprises deploy AI. We are talking about AgentAssert ABC. It's the definitive open-source framework built specifically for AI reliability engineering. If you're out there building, architecting, or managing autonomous AI agents, you already know the stakes are astronomically high right now. And well, this framework gives you exactly the tools you need to deploy with total confidence.
So let me ask you a question. How do you mathematically guarantee an autonomous agent's behavior over time? It's a pretty provocative thought, right? Because as enterprise AI scales up, unpredictable behavior is no longer just a minor annoyance. It is completely unacceptable. Regulated industries simply can't just cross their fingers and hope an agent stays on script during a 20-turn conversation. We need absolute certainty.
Okay, let's dive right into this. You're probably super familiar with standard guardrails. They're binary, they're reactive, and they basically just rely on per-message filtering. They just look at an output and block it if it looks bad. But here's the catch. Under real enterprise load, those ad hoc guardrails completely fall apart. AgentAssert ABC takes a fundamentally different approach. It provides continuous, certifiable mathematical certainty about an agent's behavior over time. It's proactive, not just reactive.
To understand exactly how this works, we're going to build this up layer by layer today. First, we'll look at the AI reliability problem. Then, the agent behavioral contract. Third, the physics of agent drift. Fourth, multi-agent pipeline safety. Fifth, scoring enterprise reliability. And finally, number 6, deploying AgentAssert today.
All right, let's kick things off with Section 1, the AI reliability problem. Why behavioral contracts actually matter in enterprise AI deployments.
Look, we all know production agents are non-deterministic. They hallucinate, and they can give totally different answers to the exact same prompt. But honestly, the bigger issue is that their behavior drifts over extended sessions. An agent might start out perfectly polite and compliant, but gradually degrade as the context window fills up. Because of this, standard ad hoc guardrails just fail under real load. What the industry desperately needs right now are verifiable behavioral contracts, mathematical certainty over mere prompt filtering.
Moving on to Section 2, the agent behavioral contract, defining the mathematical boundaries.
So, what actually goes into this so-called constitution? It's defined by Formula 9, the contract tuple. C equals P, I hard, I soft, G hard, G soft, and R. That's preconditions, hard and soft invariants, hard and soft governance, and recovery rules. Now, the absolute key innovation here is this bifurcation between hard and soft rules. Hard rules, those are your absolute red lines, like ensuring personally identifiable information never ever leaks. If a hard rule breaks, the system does a strict halt and raise. But soft rules are more about graceful behavioral shaping, like maintaining a professional tone. If a soft rule breaks, the system triggers a recover and continue action, quietly fixing the issue before the user even realizes something went wrong.
This brings us to our next layer, governed by Formula 2, the probabilistic satisfaction model. Look, because LLMs are inherently probabilistic, standard 100% or 0% software correctness just doesn't work in the real world. Instead, AgentAssert uses 3 highly precise dials, P, delta, and K. P is how often hard rules hold, which you typically want greater than or equal to 0.95. Delta is the maximum deviation allowed for soft rules, usually less than or equal to 0.1. And K is your recovery window in turns, basically how quickly the agent has to fix a soft violation, like within 3 turns. These 3 specific knobs completely replace a single clunky compliance threshold. They give regulators exactly the granular control they've been asking for.
Okay, Section 3, the physics of agent drift, modeling and bounding behavioral degradation.
To actually control drift, we first have to measure it, right? We use Formula 1, the composite drift metric, or DFT. It's a clever weighted formula. It takes 0.6 times direct rule breaking and adds 0.4 times the Jensen-Shannon divergence of the agent's action patterns. Now, why Jensen-Shannon divergence? Well, KL divergence is asymmetric and blows up the math on zero mass, and Wasserstein has no metric on categorical action spaces. Jensen-Shannon divergence is symmetric, bounded, and honestly, it just works beautifully for this.
Once we're actually measuring that drift, we model it using Formula 3, Ornstein-Uhlenbeck dynamics. The formula is dd equals alpha minus gamma d dt plus sigma dw. Okay, I know, that sounds like super dense stochastic calculus, but conceptually it's just a mathematical tug of war.
On one side, you have the AI agent's natural tendency to wander off and hallucinate, and on the exact opposite side, you have AgentAssert's mean-reverting recovery force constantly pulling it back to safety.
So, how does this tug-of-war actually play out? Well, we prove it using Formula 4 for Lyapunov stability, where V of E equals E squared. The sequence is simple. The agent naturally drifts, the recovery force kicks in to correct it, and ultimately the drift converges to a bounded stationary limit. This math literally guarantees that as long as the recovery rate is stronger than the natural drift rate, the agent will never spiral out of control. It's solid proof that contracted agents with active recovery have bounded drift. A total game changer.
Let's move to Section 4, Multi-Agent Pipeline Safety, Scaling Mathematical Certainty to Complex Systems.
When you start stringing agents together, the open-source framework handles it through Formula 5 for compositional safety. By checking 5 specific conditions: type compatibility, invariant preservation, monotone drift, recovery propagation, and failure independence, AgentAssert gives you the foundational mathematical lower bound for behavioral compliance across entire multi-agent pipelines. This is absolutely massive. It's the very first formal lower bound for behavioral compliance under composition, a foundational result for the multi-agent era.
And that brings us to cost-efficient certification using Formula 6, SPRT. The sequential probability ratio test is essentially a statistical efficiency engine. Think of it like tasting a giant pot of soup. You don't need to eat the entire pot to figure out if it's too salty, right? You just need a couple of spoonfuls. SPRT does exactly that. It stops testing the absolute second it has the minimum statistical evidence required to prove the agent is mathematically safe.
And the real-world impact of that efficiency? 150. That is a massive operational win. SPRT typically converges in just 150 to 300 test sessions. If you were using Formula 7, which is a traditional Hoeffding fixed sample baseline, you would literally need around 18,000 sessions to get the exact same confidence level. We are talking about a 60 to 120 times reduction in testing costs per single certification cycle. Incredible, right?
All right, Section 5, Scoring Enterprise Reliability, the executive metric for production agents.
That executive metric is the Reliability Index, or theta, defined by Formula 8. Theta mathematically weights and combines 4 critical things: compliance, drift stability, event frequency, and recovery success. It takes all of that unquantified AI risk and transforms it into a single, highly auditable number. For regulated industries, this serves as the ultimate deployment gate, and the framework establishes a very strict deployment-ready threshold of 0.90.
And the baseline testing really illustrates exactly why this framework is so crucial. Listen to these numbers. For out-of-the-box data scores, we tested 3 of the absolute most advanced frontier capability models on the market today in a retail shopping benchmark. GPT 5.3 scores 0.83, Claude Sonnet 4 scores 0.85, and Mistral Large 3 scores 0.79. Do you see the issue? Not a single one of them clears that 0.90 threshold out of the box without a framework. That exact gap, the gap between raw frontier capability and actual deployment-ready behavior, that is exactly what AgentAssert closes.
Finally, Section 6, Deploying AgentAssert today, bridging the gap to deployment-ready behavior. Honestly, the best part of all of this is that it's an entirely open-source framework created by Qualixar, the company that is literally defining the AI reliability engineering category. I highly encourage all technical practitioners and architects tuning in to dive straight into this. You can read the published paper and check out all the math on archive at 2602.22302. You can install the live code package right now via PyPI just by running pip install AgentAssert ABC, and you can explore the entire repository over on GitHub at github.com/Qualixar.
Before we wrap up, I want to leave you with one final thought to really reflect on today. Is your enterprise AI mathematically certified? Because in today's rapid-fire landscape, deploying without a verifiable behavioral contract is a risk you simply no longer have to take. Thank you so much for joining me for this explainer. Go check out the Qualixar open source framework and start bringing true mathematical certainty to your AI deployments today. See you next time.